Welcome to Pomodoro Joe for Tuesday, January 24th, 2023. Today we're looking at LeetCode problem 909, Snakes and Ladders. It's a medium problem. I don't really have time to read this entire problem description, so I'll just give you the basics. Essentially, we have a game of snakes and ladders with a board laid out like this example here. We start at position 1 and we move to the very highest numbered square. Now we traverse the board starting at the lower left. We move from left to right. Then we move up and we move from right to left. And we keep alternating left to right and right to left every time we go up to the next row. If we land on a square that has a ladder, we must traverse to its destination square. Or if we land on the head of a snake, we must slide to the destination or the tail square of that snake. Now our goal is, given a board, return the shortest path from the start to the end. And if there is no path, we return -1. All right, so we'll get started. We will start with a result, -1, and we will return that result. Let's set 25 minutes on the Pomodoro timer. There we go. Okay, so I will be treating this as if it were a graph traversal problem. We're going to start on node 1, and then all the connected nodes are all the squares that we can reach within one dice roll. That's 1d6. So we can reach 2, 3, 4, 5, 6, or 7, and 15. So every time we go through our loop, we will essentially put all the connected nodes onto our stack, then we'll pop them off and go to all those connected nodes. Okay. So we will start with some stack. And our stack is going to start, will just be at position 1. We also want to keep track of which squares we've visited. That's going to be a set. Okay, and while we have a stack, so that's while the stack is not empty, we will get our position, and that's going to be stack.pop. Okay, so one thing I've already noticed that I'm going to need is I'm not keeping track of the number of moves we've done so far. So I need not just my position, I need how many moves we've taken to get to that position. So this is going to be position, comma, moves. All right. Now, if our position is equal to the end position, okay, we don't have their end position yet, so we'll calculate that up here. All right, so our dimension is the length of our board, and our end position will be equal to n times n. Okay, so now if we've reached our end position, if our result is still equal to -1, then this is our best option so far. Otherwise, our result will be the minimum of either our current result or the moves that it took to get here. And then we can continue. Next we say, have we visited this position already? So if our position is in our visited, well, then we'll just continue. We don't actually want to do anything. We've already processed this position. And finally, we'll say for every dice roll, for every I in range, from the die can go from 1 to 6, so we have to make it 1 to 7 in our range, because range does not, it's an exclusive range, so it does not include 7. So this will go from 1 to 6. That means our next position is going to be equal to our current position plus I. Now this doesn't handle our ladders or our snakes just yet. So we need to do some type of adjustment. So we can say our next position is really going to be not just position plus I. It's going to be like, let's say, find destination for this position. And then once we have this destination, we'll basically just add it to our stack. So this is the next position on our stack. So what is this next position, or find destination? So this will have to tell us whether or not we just move to the next square, or if we traverse a ladder or slide down a snake. So let's create this find destination. It's going to be up here. We'll have some function, and it will take an input position. And the first thing I want to do is I'm going to convert this position into some index. So let's say this is going to be our index, and that's going to be our position minus 1. So for example, when we're on square 1, our index will be index 0. So that gives us our index for this position. Now the next thing I need to do is translate that into some x and some y coordinate to map our board, and then we have to look up what that board says its position is, and if it's -1, then we just return our position, we don't do anything. If it's not -1, then we return the destination. Well, that's going to be a little bit confusing. Calculating that x and y, it's possible, you can do it, but I think there's maybe an easier way. Because of all these like traversing left to right and then right to left and switchbacks, let's just flatten out our board. So we'll make a flat board, and that's going to be some array. And now we need to go through and build up our flattened board. So what I'm going to do is essentially grab a row from the board and put it in our flat board, then grab the next row and flip it around, put it in our flat board, and then next row. So every other row I need to flip around. So let's see, let's say needs flip. We'll set it to false to begin with. So let's see, for row, not now, for row in our board. Now one thing, I don't know how many, I can figure out how many rows based on our n, but I think what I want to do, because I'm starting at the bottom row, I really want to flip the board upside down so I can work my way from top to bottom. So let's flip the board upside down. So we're just basically reversing all the rows in their up to down order. So for every row in our board, let's see, we have some new row. And that's going to be the row, and we'll just make a copy of it because we don't want to mess with our input board. And now if this needs flip, so if we have to flip this row from left to right, then we will do that. So our new row will just equal the new row backwards. Just how we did with the board, we can do that with the row. And then if we don't need to flip it, we will just say, I think my video may have stopped recording. I'll keep going. So if we don't need to flip it, we'll just say flat board. We'll extend by this new row. And then we need to flip our needs flip because it's every other row. So needs flip is not needs flip. Okay, so now we've flattened our board. That makes finding the destination a lot easier. So if we have a flattened board, we can just return our flat board at our index. If the flat board at the index is not equal to -1. Otherwise, we're just going to return the position that we sent into this function. So that's just saying, let's look at the position we're at. If we're at 1, if our flat board says it's -1, we stay at 1. If we go to 3, 4, 5, these are all going to say -1. But if we land on 2, then we'll return our flat board at index 2, or in this case, index 1, position 2, index 1. and that's going to give us 15. Okay, so I think that's actually all we have to do. Let's give that a shot. I probably made some typos. I was working pretty fast. Yeah, let's see. All right, of course. So we need to do more than just append the next position. We need to append the next position and the number of moves that it took to get there, which will be the moves plus 1. Okay, try that again. Still got something wrong. Let's see. Oh, yes, I am not doing any range checking here, which I should be doing. So if this position is greater than or equal to our end, actually if it's just greater than our end, let's see, is it greater than or equal to or greater than? So our end position is n times n. Yes, so it's got to be greater than or equal to our end position. And we'll just return the end position. Okay. That should handle the out of bounds error. Time limit exceeded. Let's see, I must be doing something wrong in here. Ah, of course. If it's invisited, we continue, but if it's not invisited, then we need to add it to the visited. So there we go. That should take care of our time limit. And that passes. Okay, a lot of stuff to keep track of. Clearly I missed a few things along the way. Let's see how well we do. Does okay. 44% in terms of runtime, only 15% in terms of memory. Not great. There will be better algorithms than this one. This one just seems like the easiest and fastest one to explain, so that's why I went over this. I totally recommend you check out this problem. Check out the other solutions. They're available under the Solutions tab here. There's a lot of great ways to go about solving this problem. This was just one potential way to do it. I'll show you really quick. So of the other solutions I had a 42% with 15% memory, so a little bit worse than this one. And then I had a 22% with 15% memory. So far, this has been my best solution. Okay, hope you enjoyed this. Hope you had some fun. Hope you learned something. That's it for today. Hope you can write better code than I.